Recording started.
All right, good morning, everybody. I hope you guys are doing well today, or hopefully better than myself. All right, I may have to turn the webcam off here for some audio issues, it looks like. It doesn't look like the recording or the audio is caught up for everybody quite yet. There, hopefully that helped. Um, all right, so I am definitely under the weather today, so I'm just going to apologize in advance if I seem off, or if it's not my best class today. You guys kind of know why. We have a stomach bug that just hit our house super hard Sunday night, right during the middle of the Super Bowl, in fact. And then it hasn't quite left yet, so we're still on the mend, but things are looking up, so hopefully by tomorrow, we'll be better in the Xander household. So again, I apologize if I'm a little off the mark here in class today, but I'll try my best to work through it all. Um, Before we get started with 6.04, which is on polar coordinates, so we'll learn, I will have to turn my webcam on back on at some point today to show you guys how to work in that polar mode. Um, but are there any questions with our parametric mode or equations at all? I know some of the graphs weren't coming out fully like they may have shown in the answer keys when you turn your quizzes in, but that's okay. I know the parabola one was a big one. Um, I still accepted it all for full credit. So even if you didn't get the full graph in 6.03, I still did accept it for full credit. Okay, anything else before we move forward? No questions here. Okay, good. Then you will need your graphing calculator for today's class again as well. If you don't have a graphing calculator, I do have a Desmos calculator that will help you with your polar graphs. If you really like some of the graphs that you saw with your parametric equations, like all the flowers and stuff that were created, you're really going to like your polar coordinates in your polar mode. We can do some pretty neat graphs. In fact, I think the next I have a whole lesson, I think, designated for just polar graphs and all the different shapes and techniques and whatnot that we can get from our polar equation. So you'll like what's in store coming up here. Okay, so the first thing we're going to talk about, and we don't necessarily even need our calculator for this, is plotting points in the polar coordinate system. So instead of an XY coordinate plane, you're given like your R and your theta. So all of these are R and theta when we take a look at a point in polar coordinates. So R is referring to the length of your, I don't want to call it like a vector, but the length of your line, sort of. And then pi over 3 is the direction of the angle at which the point is going. So for example, in this first part here, 2 pi over 3, I start with kind of a vector in this direction, right? A starting point. And then pi over 3, I want to say is about somewhere in here, right? So the direction that we're moving is pi over 3. And then the length will be your 2. Okay. So that's how we're going to go ahead and graph that first one. Now the second one, and let's see, -1, 3 pi over 4. So I'm going to have that starting kind of vector again, right? I kind of think of that as like your x-axis, so to speak, starting kind of at the origin right here. 3 pi over 4. If we were to find 3 pi over 4, which quadrant does that fall in on our unit circle? 1, 2, 3, or 4? 2. It's somewhere in quadrant 2, so somewhere like out here, a little past 90 degrees, right? So we know that the direction in here is going to be 3 pi over 4. But now how do we take into consideration this -1? Well, -1 means we actually have to extend it past the starting point in 1, the length of 1. So that's where it gets a little bit weird with that r value. So again, we still want to draw this direction angle first, but then if there is a negative length, that means we move down from the starting point on that same kind of diagonal that we were going here, but we move down in the length of 1. So technically this is a -1 down in here. All right, and then the last one with -45 degrees, what do you think of when you hear -45 degrees? There's two different things you can technically think of when we go to graph this last one with that direction. What's the first thing you kind of think of with -45 degrees? You can add 360 to that, yep, to make it a positive, most definitely. What would that be if we were to add 360 to it? Around 315, or not around 315. It is 315, which is in quadrant 4, right? So somewhere down here. So we can look at it as this is 315 degrees, or if we look at it from the inside part here, that's -45. So you can technically go the clockwise direction and get that -45 there. Now it is a length of +3, so since we technically started there and we'll end somewhere out here, we got to make sure that that has a length of 3. Now don't confuse that with the -1 just because we're moving down here. That's still positive. If it were negative, we'd have to extend it back in this direction, right? So just because it's kind of in the same area that part B was, we didn't extend it past the starting point here. So if it were negative, we would have reached out back in this direction somewhere. So this is still representing a length of +3. Any questions with those graphing? It is really strange to think of that, isn't it? That's generally not what we're used to. But yeah, definitely a new way of looking at things. Questions with that before I move forward and we talk about how to find these points algebraically. So the other weird thing is we are working in a circle, right? So just like our unit circle, we can get more than one representation for a point. So these are not unique points by any means in our polar coordinate system. We can find different ways to represent this same point using some algebraic methods that are going to come up on the next slide. So in your polar coordinate system, what you have to think of is you have these axes here, and it's actually made up of a bunch of circles like around here, and this is what we're plotting on to find those points essentially. So it's kind of weird to think about, but that's essentially the type of graph that we're working with when we're in our polar coordinate system. So we are working on a circular basis. And that I probably should have let off with that because I could have just graphed them right on here then. So like a length of 2 would be right there. And then you can go ahead and follow the rest of those as well. But let's move on and talk about how to find all polar coordinates of a point. So much like our angles with our like radian and degrees, we could, on our unit circle, we could find additional points by adding or subtracting 360. We're going to kind of apply that same concept here to start us off, except we're working with radians. We're not given degrees too often, although we do run into degrees once in a while. We saw that on the last slide. But they give it in terms of radians versus degrees here. We can keep the r, but we can find additional theta points by adding 2n pi. And basically the n can represent 0, 1, 2, 3, any integer really. So negative, 0, or positive, n can be any of those values. So really you're adding 360 or 2 pi onto that, or multiples of 2 pi onto your theta. So this first one is really nothing new for us. So we'll start with r, and then generally we'll add 2 pi or 360 onto that theta to find an additional representation of the point. The next one is a little bit weird though. We haven't seen this form quite yet. And what we can do is we can take negative r, so the opposite of r, and then to our theta, we can add 2n plus 1 pi. So essentially what that is stating is if we are starting like out here somewhere, if I were to do the negative r of that, it would be back here, and then I'd have to add on kind of that 2n plus 1 pi to get back to the starting piece. So that's kind of what that second piece is looking at there. All right, let's go ahead and take a look at an example finding all polar coordinates for a point. If the point P has polar coordinates 3 pi over 3, find all polar coordinates for P. All right, so the first thing we're going to do is we're just going to follow this first rule of keeping r and then adding 2n pi to our theta. Now it does say all polar coordinates in our question, so we want to make sure we leave n in there. That way we can make sure we hit all of the bases. Sometimes they'll just say find 2 additional polar coordinates. If it says just find 2 additional polar coordinates, that's when you can start creating values for n to substitute into that formula. But if it does say to find all polar coordinates, you want to leave it pretty generic to cover your bases. All right, so we're going to keep the r. We're going to have pi over 3 plus 2n pi. And let's go ahead and clean that up a little bit. Let's get a common denominator here. If I get a common denominator in this second piece, that's going to be a 3. So I'm going to have to alter this to be a 6 over 3. It looks like. And maybe I can add those. Can I add those together? If I take out a pi, I think I can take out a pi from that, right? And get a 6n plus 1 or 1 plus 6n. I think that's about as basic as I can probably get it there. I can't add those like terms because I don't have an n in front of this pi right here. So I think that's what Tommy was for, or no, that was for a different one. So I can't add these two strictly together because there's no n variable in front of this one. But if I factor out this pi, I have the 6n plus 1, or technically 1 plus 6n, left behind in the parentheses. And that can be all over 3. So this is one way to kind of represent that first choice. Any questions with that before we take a look at the second option? Okay, the second option then is taking the opposite of r, which is going to be negative 3. We'll take pi over 3 plus 2n, whoopsie, n plus 1 pi. Again, I'm going to go ahead and multiply this by 3 over 3 so that we can get a common denominator there. And if I want to, I can factor, so I can combine those two fractions there. I can take out the pi again, but I'll be left with 1 plus 6n plus 3 all over 3, which technically will just be our 6n plus 4 on the numerator there. Eeks! Running out of room. Okay, hopefully I was able to squeeze that all in there okay for you guys. I know it was a tight squeeze though, for sure. So here is a second form to denote all of the points that fall at 3 pi over 3. And again, we had to leave it generic with n in there so we can make sure that we hit any and every value that n can possibly be. Okay, any questions with these two formulas? I know they seem a little bit weird, but when we get to use them a little bit more, they're not too bad. All right, we're going to keep pushing forward then. So we found how to find additional points for a polar coordinate. The next thing we have to learn is how to convert them back and forth. So can we go from rectangular coordinates, which is our x, y, to our polar coordinates, which is r, theta, and vice versa. So much like our parametric equations, we switch back and forth, right? We went from parametric equations to rectangular equations by eliminating the parameter. We don't have eliminating the parameter here. We do have formulas to help us convert back and forth though. I don't think so. I'm not quite sure. So the 6n, they're only 3 off. I'm not quite sure if that is a difference with the r. I don't think so. I think it has more to do with this 2n plus 1 in here. So this plus 1 feature versus just the 2n. So I don't think the r has any effect on it only being 3 off. It's going to be this plus 1. Yeah. All right, so this actually isn't going to be too bad, believe it or not, as long as we have these formulas written down to rely on. So definitely, if anything, make sure that this whole box up here gets put in your notes so that you can look back on it. The first two pieces of information right here are going to help you go from polar form to rectangular form. So this helps you go to rectangular, and I should probably write that on top here. And then the last two chunks here help you go to polar. So if you're starting in rectangular, these two equations are going to help you convert that to the polar coordinates. All right, so the first example we're looking at here, it says use an algebraic method to find the rectangular coordinates of the given polar coordinates. You may have to approximate your answers when using your calculator. All right, so to find the x and y, we're just going to, we start with polar and we're going to rectangular. We've got to use the equations in the orange. So we'll start off with x equals r, which is 3, times cosine of 5 pi over 6. So you will need a calculator here. And go ahead, type that in. Make sure you're in radian mode. So we've been working with degrees for a while, so before you actually go ahead and start typing this in, make sure you're in radian. And what do we get approximately for this first x value? Yeah, we should get a negative 2.598, so we're going to round that to a negative 2.6. All right, we'll express this as an ordered pair as soon as we find the y value. Y value is very similar, but remember the y is referring to the sine, so we're going to do 3 sine of 5 pi over 6. What's the approximate there? 1.5 looks like. All right, everybody agree with those? We'll go ahead and put those as an ordered pair. Negative 2.6, 1.5. And we now change that or switch that to the rectangular coordinates that we're used to. All right, let's go ahead and do the same thing with part B. So let's start with the x first. So it'll be 2, and this time we're dealing with degrees. So now you need to switch your mode again because we have to pay attention to the details. So we'll switch the mode to degrees. And then we'll type in our values here. What do we get approximately? Anybody? Okay, yep. And Isaias already has the y, so I'll let you guys go ahead and type that in for the y, but remember use sine versus cosine. Can anybody second that 0.68? Awesome. So not too bad when we're starting with our polar coordinates and we're trying to switch that to our rectangular. All right, let's see if we can go ahead and do the same thing, except the other way around. If we're given the rectangular, can we switch that to our polar? All right, so we're always going to start by finding r first. So make sure we're using this right here. R squared equals x squared plus y squared. A lot like the Pythagorean theorem, right? And if you're thinking about it, you can drop down a triangle from that r, and the r would be your hypotenuse. So let's see. What are we going to get here? And we'll probably leave it as a square root. square root of 2, right? Because 1 squared plus negative 1 squared is 1 plus 1, which is your 2. All right, so then we are left with finding theta. So I believe it's tangent of theta. Excuse me, I'm just going to go back a slide here. Tangent of theta equals y over x. So tangent of theta is y over x. Anybody remember how we can get rid of the tangent that's in front of our theta there? You've got to do arctangent. Yeah, so essentially to find theta, you're going to be doing tangent inverse, so the negative 1 power of y over x. So 1 over negative 1. Yeah, and this is going to, if you're, we're probably still in degree mode, right? So if you have that negative 45 degrees, that's totally okay. We can use our unit circle. This one's actually on the unit circle quite nicely. Negative 45 degrees is going to be at what, negative pi over 4. Okay, there's one thing, oopsie, that was a bad theta. There's one thing I missed up above though that I'm going to backtrack real quickly to. And that is when I found my r. Technically, when I take the square root of both sides, what should I put in front of that? A plus or minus. So technically, I should put a plus or minus here. And that's going to help me find additional points for that r. So I do think that a good starting point would be your negative square root 2. So generally we start with the smaller of the r values along with the smaller of the theta, so negative pi over 4. Now to find additional points here, we can use that negative r theta plus, was it 2n plus 1 pi, right? I think that's what it looked like for that second option. And we're using the second option because we also have that positive square root 2. So if that's the case, to find the other alternative form, we need to use that opposite r formula. So pi over 4 plus, we're going to use 1 for n, so that's going to be a 3 pi in front of there. Hold on one second. I just want to make sure I'm getting this correct. Okay, so if we do, I think that's going to be a 3 pi if we make n a 1, right? So 2 plus 1 is 3, and then we need a common denominator of 4, so technically that would be a 12. And it looks like that would be an 11 pi over 4. That's not exactly what they had in the book, so I'm going to have to go back and check that. They had a 3 pi over 4, so I'm going to have to verify on what they did there to get the 3 pi over 4 versus an 11 pi over 4. But we're going to go with this for now. because this is that formula that they gave us there. Maybe they used a different value for n than what I chose. Maybe they used 0 or something. There is multiple forms, remember, so it's not necessarily a wrong answer. It could just be a little bit different version of the point. Okay, but we'll go ahead and count these two as two of the polar coordinates. Obviously, we can tell that the polar coordinates are a little bit more challenging than finding the rectangular coordinates, right? I got the 11 from -1 plus 12. So when I added the numerators together, once I got the common denominator of 4, -1 plus 12 would be an 11 pi over 4. So that's coming from this right in here. So I had to change that 3 pi to a 12 pi over 4 with using the common denominator. Yeah. I know, sometimes those adding and subtracting of our fractions can get us. Okay, I'm going to skip over part B right now. This is from the book, obviously, example 4. If we have time at the end of class, we'll come back to this one and we'll work on that. But just for time's sake, I want to make sure I hit the last couple of topics still for the lesson. All right, and the next one we're going to take a look at then is very similar. We're going to convert r equals 4 secant theta to rectangular form and then identify the graph and support your answer with the polar graphing utility. So I will show you on our calculators how we can graph in polar mode with this one. First we've got to convert it. So to convert it, I noticed the secant theta. What we're used to is having r attached with cosine or sine. So I'm going to divide both sides by secant theta, which seems a little bit weird because in the past we always tried to isolate that it's by itself. But now we're going to divide by that so we can isolate the 4. 1 over secant theta is the same as what trig operation? So 1 over secant theta is the same as which trig operation? Not really trig operation, but which sine, cosine, or tangent, which form is that? 1 over secant is the same as, not cosecant, but cosine. There you go. So technically we can write that as r cosine theta. Yeah, you were close. I think that's probably what you were leaning towards was the cosine. But now that we have it r cosine theta, we can go back to that table that I had you write down. And we know that that is going to be an x, right? R cosine theta equals an x. So if we can get either r cosine theta or y sine theta as our answer and then equals some number, we can then transform that into an x equals or a y equals equation. So in this case, it's going to be a vertical line through x equals 4. Okay, on to the fun stuff now. Let's grab our calculators and verify that. So in your mode, we're going to go ahead and I don't believe it matters if we're in radian or degrees, but I am going to switch over to radian mode. And then where it says parametric, because we were probably in parametric from the last lesson, we want to scroll 1 over where it says POL. POL is representing our polar mode. So when you have that highlighted there and kind of blinking, go ahead and quit. So second quit goes back to your home screen. Or if you wanted to, you could go to Y equals right away. All right, and you'll notice that instead of Y equals, you have R's. So it transformed that into your polar coordinates there. So we'll go ahead and type in what we originally had. R equals 4 secant. Now remember, secant is not an option on our graphing calculator, so we got to do 1 over cosine when we type that in. So that's kind of one disadvantage, is that we don't have the secant to plug in, so we got to make that as 1 over cosine theta. And then you can go ahead and hit graph. And we did verify that is in fact a vertical line through x equaling 4. You might as well leave your graph. You got an error? Leave your calculators in the polar form because we're going to need it for the last group of questions for today. Besides Tommy, did anybody else have troubles with their graph? Yours worked out just fine. Isaiah's has worked out just fine. All right, for those that don't have a graphing calculator, and I would double check. Okay, didn't put in theta. Good. I was going to say double check for errors when you typed your equation in. That's always the first thing we want to look for if we do get an error. I have the graphing program in Desmo, so 1 second here. Yeah, I had a link and then all of a sudden it must have changed on me for the Desmo. So let me see if I can Google it real fast. Here we go. I think this will be okay for the Desmos. So all you have to do is in that first one change it, so erase it essentially, and do 4 secant and then your theta or secant. Yeah, and I'm not quite sure. How to get our theta in there, I'm sure. Oh, you have to go to the ABC and then it's right underneath the P. So you have to use the actual keyboard function to get your theta in there if you're going to use the Desmos. And you'll see that that does come up as a red line. All right, everyone got the graph to work out okay then, hopefully? Okay, like I said, I do have another graphing one. It's a matching activity. So we'll make sure that everyone is good to go with that matching activity before we leave today and can at least graph, okay, in their polar mode. Before we get there though, I want to take a look at a little bit more complicated equation and converting that to polar form. All right, so we have essentially what's going to be a circle that's not centered at the origin. It's centered at 3, 2, and with the radius of the square root of 13. That's what it kind of looks like here. But we need to convert this equation to polar form. So to convert it to polar form, we actually have to distribute and expand each set of parentheses here. And I know it sounds weird, but we need things to be termed of x squared and y squared, so we can piece that together to replace it with an r squared. And then if we have an x and a y, we can hopefully replace that with the r sine theta and the r cosine theta for y and x respectively. So let's go ahead and distribute this. Check my math because obviously I'm not on my A game today. So when I expand that, I think we'll get an x squared minus 6x plus 9 for starters. And then when I expand the second one, a y squared minus 4y plus 4. All right, does that look good? Hopefully. I'm going to start moving anything that's not an x or a y, so my constants, over to the other side. So essentially, let's subtract the 9 and subtract the 4. I think that's going to bring me back to a 0 over here. So what I did is I moved this term to the other side and I moved this term to the other side. Now the next thing I'm going to do is rearrange what's left on the left hand side. So I'm going to group the x squared plus y squared together. And what can we replace x squared plus y squared with in our polar form? What did that equal? It equaled an r squared. Good. And then it looks like we're going to have to replace the x and the y. I'm going off of memory here, but x should be r cosine theta, correct? And then y should be r sine theta. Okay, so as long as we can group the x squared and y squared together, that's good news for us. Then we can go ahead and replace that x and the y. All right, it looks kind of weird because we don't have an r equals at this point, but what do all three terms have in common that I might be able to factor out on the left-hand side? They all have an r in common. So if I factor that out, I'll get an r minus 6 cosine theta minus 4 sine theta. And now I can set each set of parentheses equal to 0 and solve. So I do have the GCF, that factor of r that came out. So we'll do r equals 0, but that's just a point at the origin. And we know that r equals 0 is not the equation for what we had up there in the rectangular form, right? That is not a point at the origin. So that gets thrown out. That's not a possibility. Now if I take what's inside my parentheses here and solve for r, essentially we'd have to add 6 cosine theta to both sides and add 4 sine theta to both sides. That is a much better possibility of a circle not centered at 3, 2. So let's go ahead and clear out our y equals area. And let's type that in. 6 cosine theta plus 4 sine theta. And we'll hit our graph. Yeah, pretty good. It looks kind of like a circle. And probably centered at 3, 2 as well. Mine looks a little bit oblong, kind of weird. I was expecting a little bit better circle, but it could be the dimensions at which we're viewing that. As long as we all match together, that's the important piece, right? And it does match up to that rectangular form somewhat that we were expecting. So this is what we want to go with for the polar equation. So that one wasn't actually quite as bad as some of the other stuff that we've seen. Any questions with that one before we finish with the graphing matching section. All right, let's make sure we're really comfortable then. So we got A, B, C, and D. Let's divide and conquer. And I have 4 equations down here. Let's just put an A, B, C, or D behind them. And if you guys do the same one that somebody else does and you agree, put that letter after it anyways, just so I know that you guys are coming up with the correct graphs. So go ahead. Remember cosecant though, that is not a function on our calculator, so you have to express that as 1 over sine. All right, go ahead, try some of those out. When you have a graph that matches, put the letter behind it. All right, what you guys have on the board is exactly what matches my answers. So by the looks of it, you guys are probably pretty good to go with graphing in your polar coordinates. Everyone's calculator seems to be matching up there, which is good. Any questions with our polar coordinates? If not, give it a go. We are going to spend a little bit more time with these polar coordinates as we venture into 6.05. I think we'll be taking a look at the graphs more specifically next with those and exploring the different types of graphs we can create in polar mode. So that'll be fun. That's all I really have for you for 6.04 though. If you do have any questions, bring them to class on Thursday. We'll start out with those. Otherwise, have a great rest of your day, you guys, and I'll see you again Thursday morning. Bye, everyone.